All right, so I'm going to go through these slides, which again are posted to Google Classroom. Now, really have 13 slides. So the one I'm going to start with is not actually on here. That's center mass. So I'll tell you guys a bit about center mass. It's kind of a segue between what we did before the break, which was momentum conservation, and what we're going into. So give you guys a few different perspectives on this. One is kind of a mathematical tech perspective. That's exactly what you guys are looking at. So if you want to say, what is the center mass between, say, some set of objects, just to strip it down a bit, suppose you got like two objects and they're like different masses. So you got a big mass and a little mass, right? And the way you did it is basically take a weighted average, right? So to get the center mass between these two objects would be somewhere in the middle, but closer to the larger object. Kind of makes sense, right? And if you want to spell it exactly, figure out exactly where it is, say along one axis, this would just be one axis, okay? You take each mass, multiply by its location, okay? So, what is this location? This could be location 0, or location 0 might be over here, and this might be a small location. You can define location 0 wherever you want, but it turns out it doesn't matter. Each mass times its location, add them all up, right? That's what sigma means, right? Add them all up, then divide by the sum of masses, and that'll give you the center mass. Now, this is along one axis. If this was a two-dimensional plane, then you could do that for an x-axis and a y-axis. You could figure out center mass that way. Now, what does this have to do with what we've done before and what we're going into rotational dynamics? Right, well, I got this foam board cutout. Right? It's this weird shape. I got a whole set of these that are all different weird shapes. This one's kind of a T-type shape. Right? Shown for the video there, but show you guys it in class here. I've got a multiple choice option for what the center mass could be, right? A, B, C, or D. Okay? So I have you guys do an activity like this sometime here pretty soon. So the center mass is one of those points. Now, how can you find it? Well, if I take this into the air and I spin it, then it should spin about the central point. Now, it's kind of hard to see, but so like I take this and I chuck it through the air like a projectile. It's going to go into like a parabola path, like a projectile path, right? But actually only one point will, because we've got like a billion different points of this all moving along the own crazy path, right? If I pick this point and I put an LED light on it and watch it go through the air, thing like a spiral shape. But there's only one point that will actually make a perfect projectile parabola. It would be the center mass. Another thing that will distinguish center mass is, say that I'm going to take the string with the binder clips on it. I'm going to clip one end to some random point on this foam board. Okay. And the other binder clip I'm going to use as a weight. It's just going to hang straight down. And that will always hang through the center of mass. It will always hang through the center of mass. So, okay, so it's kind of hard to tell there because I'll line pretty close. But looks like probably either maybe point D, maybe. Okay. But I'm hanging like from here. This should tell us. You see how that string is hanging through point D and only point D? Okay. I can pick any point on this whole foam board. Okay. And it will always hang through point D. There it is again. You see it's hanging through point D. Okay. So again, I've got a whole set of these foam boards, weird different shapes. And I'll have you guys do this someday yourselves. Okay. One other way you can figure out center mass, it's always the point that it's going to balance on. Now we figured out it's point D, right? Let me try this. I'm going to turn this upside down, balance this on my finger. So I'm doing this blind, okay? But there's some point where it's going to balance. Looks like it's right about there. All right, so let's see. Is this actually point D? It is. It's point D again. So for the video, there we go. So there's a bunch of ways to get it. So you can get it mathematically this way. You can hang it with a string and the weights. You can balance it on your finger. Okay? And you can also throw this through the air, and whatever point it's spinning about, it should be spinning about point D, and point D would actually make a perfect parabola shape. Okay. All right, so save that one day. This also ties into torque, which we're eventually going to get into, but so hold on to this idea for later. Okay. All right, maybe kind of a better way to start this presentation would have been this right here, okay? Rotational analogs. So everything that we've done so far in this class in a linear sense has a rotational analog. Actually, we've done some rotational stuff before, because back when we were doing gravitation, centripetal force, and orbits, we had to do some rotation stuff. So you guys are familiar with the kinematic variables. You guys remember this turntable? Right? These Roosevelts on here, throw them on here, give this thing a rotate. Well, it's just about positive direction, counterclockwise. Okay, like that. Okay, so it's going around. And we're saying, so time's still time. So taking a long second, so that's still the same. And instead of saying how far is something gone in meters, now we want to say how far is something turned. You can measure in degrees or radians, but radians is a better way, especially if you're applying equations. Okay? Instead of saying how fast in meters per second, like radar gun speed, let's say how fast is it rotating, radians per second. Okay? Like the Earth, for example, spins one rotation every 24 hours. You could convert that to radians per second. Okay? If something's speeding up or slowing down, if it's a car, like somebody hitting the gas pedal or the brake, that'd be meters per second squared. But what about like speeding up or slowing down that turntable? It could be speeding up spinning or slowing down spinning. Okay? It could be alpha. And those are all, you can take these top 4 kinematic values and tie them all together with these 3 kinematic equations. You can also convert back and forth between linear and rotational values if you know where something's situated. Like if I put a coin right on the outside edge, it knows radial size. You could either multiply or divide by radial size depending on which way you're going, like linear and rotational variables. Okay, now that's all review. We've done this rotational kinematic stuff before. You guys have seen that. Okay. But what about these last 3 lines here? Now here's where this is going to extend to new topics. Okay, we're going to bring in torque and angular momentum, and also rotational inertia. So rotational inertia, torque, angular momentum. Okay, those are going to be the new topics for this section. Okay, guys, good. All right, so yeah, a bunch of these slides upcoming one by one. Okay, gonna look at these. So let's start with the rotational inertia. That's what capital I is. It's inertia, but in a rotational sense. Okay? It's sort of analogous to mass in kilograms. You guys remember back in the day, like Newton's second law of motion, if you put a force on a mass, right? See, like if it was a small mass for some force, huge acceleration during that force, right? But a large mass, right? It's really hard to move a large mass because there's so much inertia in a linear sense. In fact, if it has like 3 times the mass, it has 3 times the inertia. Okay? But in a rotational sense, it doesn't just matter how massive something is, it also matters the location of that mass. So give you guys some examples. How about this example? You guys have a pencil or a pen? Okay. If you try to balance it on your finger, can you do that? Can you balance a pen or a pencil on your finger? It's like nearly impossible to do, right? Nearly impossible, but I can't do it. I don't know if anybody can. But what about a meter stick? What if I take a meter stick and I try to balance this meter stick? I'll do this off camera. But this one you can do. And so maybe next time you guys back in the lab area have some meter sticks, try this out. And you probably do this for a long time, right? So why is it easy to balance a meter stick, but nearly impossible to balance a pen? Okay. Part of it has to do with mass, but a lot of it has to do with like, how that mass is distributed. Like the pen, here's the center mass of the pen, probably right about here, right? That's wherever you can balance it, probably right about here. Right? That's only a few centimeters from where I'm holding it. But that meter stick, I bet the center mass was about 50 centimeters away from that point, right? You know what else I have here? I'm going to tie this back to that example too, but I have a couple of meter sticks with some weights taped on. This guy has these weights taped right in the middle, and this guy has weights that are taped on the ends. So I got one in there, and then one on the other end here. Is that right? So let me draw those on paper, and then I'm about to pass these 2 meter sticks around, but there's something I want you guys to feel. So let me do a setup here. Okay. So got a couple of meter sticks. That themselves are pretty well identical, and same material, same mass, same length, the whole deal. But this one here has a couple of masses that are taped pretty close to the center. Mass, mass. Okay? And the other one has the same masses, just taped at different location. Okay? Now, if I was feeling those two, I'll do this off camera. I'm feeling these two. Do they feel like they have the same mass and the same weight? Yeah, they same mass, same weight. Right? What if I launch these like javelins, apply a force for some time or some distance, think they have to go through the air, look pretty well, same location, land at the same distance, right? Same motion? I think so, right? But what if I take these, grab them at the center, and start rotating them like this? Right? You guys see this one? Really easy to change the state of motion. And this one, really hard to change the state of motion. So it kind of gets in front of the camera. Right? This one, if I grab it right at the center, go. Really easy to change state of motion, that guy. Okay. This guy with the weights at the end, really hard to change the state of motion. Okay. A lot of rotational inertia, right? A lot of inertia in a rotational sense. Got pass these around. You guys can get your hands on those, feel those. Okay. really feel that difference. Let me complete this picture here. So just grabbing these right at the middle, rotating this, and this top one, really easy to change its state of motion, just like no problem at all. Okay. So this one down here, grab this guy at the middle. Okay. Try to rotate this guy. Woo! It's really hard to change state of motion. Now, all this rotational stuff we're doing, you can tie back to linear principles. So in a linear sense, you guys see how these masses are not moving that far, but these masses have a long distance to move, right? So, okay, so maybe that ties into it. But what's the rotational formula that would tell you how much inertia it has? Okay? So rotational inertia is equal to, okay, now for a single point, it's called mr squared, okay, where from this pivot point in the middle, I see that each one of these masses has this radial distance r. Okay, and same story down here. R. Okay, so if I take this mass times this radial distance squared, okay, that could represent how much rotational inertia it has. Okay. And then what about the fact that there's two of these guys? Well, you can just add them up. You do this mr squared plus this mr squared, right? You get the total rotational inertia. Right? Maybe the meter stick itself could add a little bit too, but we're about that. Okay. So I can say sum of them r squared, right? Like I'm adding up all the bits. In this case, this mr squared plus this mr squared. Okay. And the fact that this radius is so large for this one compared to this one can have a lot more rotational inertia. Like I said. Okay. Well, now go back to like trying to balance the pin on your finger. Right. So pin on your finger is kind of like this top scenario because it's so short. Right? Here's mass of the pin. Here's the radial distance. Tiny. Right? Such little rotational inertia. It's really easy to change the state of motion. Really easy to topple over. Really hard to keep it upright. But take that meter stick. Balance that meter stick. Woo! Its center mass that's 50 centimeters up. Okay? Probably a little bit more massive too, right? More massive, 50 centimeters up. A lot more rotational inertia. Really hard to change the state of motion, really easy to keep balanced. Okay? You guys ever seen a tightrope walker? Okay. So let's say you have a tightrope. Here's a cliff edge, here's a cliff edge. Okay, got this guy trying to walk a tightrope. Okay. You guys ever see them? They have a lot of times they'll carry a big old pole with them. Why would they carry like a big old pole? Because it gives them a bunch of rotational inertia. A lot easier to maintain balance when you're carrying that big old stick. Okay. You guys got that idea? Okay. All right. All right. So that's this concept here. Oh, look at that. Mr squared, the sum of, right? Like you're adding up points. Right? Oh, and the unit for that would be kilogram meter squared. Now, what about though something like this turntable? Give this turntable a spin. Now, I know this is like an octagonal shape. Looks like an octagon, but it's pretty close to a circle. You guys think pretty close to a circle? Okay. And it has some width to it too, right? You guys see some width going on here, right? So give this thing a spin, and it has some mass. That's distributed. I'm trying to rotate this thing. If I draw this out, and so I've got this turntable. Got some width to it. It's got here's like the center that it's rotating about. So here's the axis of rotation. Got some mass. Got a radial size. Oh, it's like R. What's that, right? And say I have a string wound around this, and I'm pulling with some force. Right? About to lead to torque. Haven't quite got to, but leading up to that. Okay. How much? Like how fast is that? Speed of spinning, sort of. Okay. I can sort of change this by throwing a mass on top of this. See if I put a mass right at the center. It's really easy to get it rotate. But if I put the mass bar out, it's a lot harder to rotate. Put bigger force to get it going. Okay. But just the wood itself already has some rotational inertia. But how much? Well, here's the thing. I could split this into like a billion different points. Right? I can sort of show that here. So this solid disk has not just points at the radial distance r, right, which if it were a ring, but it also has some points distributed towards the center. Right? It's got like all these points. I can break this to like a billion different points. I can put like a billion different dots on this. Okay? So sort of like a calculus type thought process where you're just going to infinitesimals. Okay? And some of these points actually do have individual rotational inertia of mr squared. But a lot of these points are like closer to the center, which would be m times something less than r squared. You guys get it? There's some aggregate effect for certain shapes. Like for a solid cylinder rotating about the central axis, it has to be less than mr squared, right? Because you guys can I see that? So what's like the aggregate effect, right? Well, that's what this next slide is for. Rotational inertia table. So different shapes. So remember, for a single point, like a point mass, it's just mr squared. So got that established. This mass times this radial size squared. Actually, for a ring, it would be the same story. As long as the ring is also rotating about the central axis. Because this point's mr squared, this point's mr squared. They're all mr squared. They're all equidistant from the center. So these have to be the same. Right? But here's the situation I was showing with the turntable. You just take this, make it flat. It's the same idea. Okay? It's rotating about the central axis and just turn it vertical, same idea. Okay? You guys see that the aggregate effect is less than mr squared? Okay? It ends up being 1/2 mr squared. No, if you go like do the math on it. Okay? Or if you turn it on its side and turn it like a coin, okay? Like a quarter mr squared. Okay? Yeah, let's get a look at that. Right? So like instead of the coin rotating this way, okay, but the coin is like rotating this way, right? The big spin. So might come back to that later. Okay? Here's some other shapes. Right? So if you have a rod rotating about the center, it's being a 12th in L squared, where L is the full length. Okay? If it's rotating about the end, it's 1/3 in L squared. By the way, these two are related to each other by something called parallel axis theorem, which I'll tell you guys a bit about. Okay? And here's a solid sphere, and here's a hollow sphere. Okay? And the big picture idea that I want you guys to see is to like compare some of these things. Okay? So if you have like a single point or mass all equidistant from some point, it's just mr squared, right? But if you have the mass distributed closer to the center, it's got to be less than that. It's got to have not as much rotational inertia. Okay. But what about if you compare some of these? Like, how about here, 2/5? Is that like 0.4, like 40%? Right? So the bowling ball has a lot of its mass distributed really close to its own center mass. Okay? Compared to the basketball, do you think the basketball should be somewhere between the bowling ball and the ring? Do you guys think? Okay. The basketball is kind of somewhere in between because basketball is hollow, right? Hollow sphere. Right? And it definitely is. Right. So here's 0.4 2/5. Here's 0.67 2/3, and here's 1. Right. So basketball is between this guy and this guy. Okay. Right, guys good? All right. So 2 different ways I want to go with this. May expand your guys' imaginations a little bit. I don't know if this is ever really going to come up again in this class, but at least I want to put this out. I'd say this is here. How do you guys think about this a little bit? Right. Something called parallel axis theorem. And if any of you guys are going to go into engineering in college or take physics in college, then you'll almost certainly see this. So what if you have something that's like revolving, right? Like the basketball itself, its own rotational inertia rotate about its central axis. Like if you try to spin it on your finger, it's like 2/3 mr squared. So that's all fine and good. Okay. But what if it's like revolving around here? Right? Well, now it's probably a lot closer to the situation of like a point mass, like this m times this d squared. Okay? In fact, that's all you do. You just add those two together, right? So you got the 2/3 mr squared, this rotation, plus this md squared, this revolution, and you just add it all up. Okay? And what's one place that could be particularly useful is like a ball rolling on the floor. Because about its own central axis, got its own rotational inertia. So for a basketball, it'd be 2/3 mr squared. That's just like spinning on your finger. It's 2/3 mr squared. For rolling on the floor, the pivot point is actually not the center of the basketball. The pivot point is actually down here. Is that what it's actually rotating about? So you have to add the md squared, but the d in this case is r, right, because it's rolling about, right? And put it all together, it ends up being a larger rotational inertia. So if you give this ball a push, or you kick it or push it to get it rolling around on the floor, it's supposed to be like some empirical measurement. You would actually probably measure something a lot more like this, 5/3 mr squared. Okay. All right. Guys, good with that so far? All right. Next idea is going to tie into torque. sometimes called a moment. Uh, so I usually call it torque. This is here. My classic go-to example is every time you open a door. Right? So I know it's showing like a nut and a wrench here, but could this be like a door, and this could be the hinges, and this could be the handle, right? Hey, why is the handle always opposite of the hinges on the door? Why not put the handle right in the middle of the door, or the handle really close to the hinges? You guys ever try to do that? Try to open a door by pushing really close to the hinges? Right? Is that really hard to open the door? Yeah, it's really hard to open the door, right? Okay. So something to do with like not just how hard you're pushing the force, but something to do with like the location of that force will give you a torque, right? Which is like a turning moment. Okay. So the physics formula for that is just R cross F. Right? You just multiply the two together. This radius times this force. Right? Well, actually, that cross is a special kind of multiplication. It's called a cross product. And what that means is you only multiply the perpendicular components. So suppose you have like a really rusty nut here. It's been rusted over forever, and you really need to loosen this. So you put your wrench on there, like, you're really trying. It's like, okay, well, how can I help myself out to maximize my chances of like breaking the rust? Well, one thing you can do, obviously, is like push as hard as you can push, just to like increase the force, maximize the force. Another thing you can do is maximize this distance, right? Increase your radial distance, push as close to the end of this as you can. The third thing you can do is try to make this force perpendicular to this radial arm. If you make them exactly perpendicular, see, only the perpendicular part actually does anything, right? Causes any kind of torque. Right? Like if you go to the door, say here's your hinges of the door, here's the door handle, you start pushing or pulling like parallel to the door, it's never going to rotate the door, right? So only the perpendicular part actually does anything. Okay? And you can call that like RF sine theta, right? Now, careful about the sine theta bit because you have to say, well, what angle are you actually talking about? We're talking about the angle between the two vectors, right? This R and this F, this theta, which is equivalent to this theta. Okay? But do you guys see if you were given this angle, you'd have to do sine, there's a, not sine, but cosine, right? If you were given this angle instead. Right, so be careful about that, what angle you're given. Okay. Right, is that right? All right, now torque is equal to R cross F, sure. Right. It's also equal to I times alpha, and that is actually analogous to Newton's second law of motion, but now it's in a rotational sense. Okay. So you guys remember Newton's second law of motion, F equals ma? Okay. So rotational inertia is analogous to mass, right? How much inertia does something have? Right? Angular acceleration is analogous to linear acceleration. And now torque is going to be analogous to a force, right? Just not in a rotational sense. So you can take this R cross F and you can multiply by I alpha and you can solve for stuff. And I'll give you guys an example of that. I've got an example started right here. So I've got a turntable rotating about central axis. I'm going to apply a I'm going to wind a string around. You guys see a string? Zoom, 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 wind around. Okay. I'm going to pull on the string with some force. And it's going to cause it to speed up spinning. If it starts from rest, it might go like, and it starts speeding up spinning. And now what rate can it speed up spinning? And I can use exactly this to solve that question. Okay. So I know that torque is equal to R cross F, and it's also equal to I times alpha. And in this case, I'm solving for alpha because the question is how fast is it speeding and spinning, right? Let me throw some numbers in here. Let's give this thing a mass of like 3 kilograms, 3.0 kilograms. Let's give this thing a radius of like 0.70 meters. About that big old turntable. Okay. And let's say I'm applying a force of like let's say 5 newtons. How about that? 5 newtons. Where's my spring scale? Okay. So pull this. I'm pulling with like 5 newtons of force right about there. Constant 5 newtons. Okay. This thing's gonna speed up spinning. Do you guys see how this is like perpendicular? Right. That's one reason I like this example with the turntable and the string, because this radial size and this force will always be perpendicular. Okay. So I don't have to worry about sine of 90 degrees. Sine of 90 degrees is just 1, so it's all good. Right, so I'll have a radius of 0.7 meters. Let me just bring this right down here. 0.70. Actually, I went through in one more step. Okay, got R times F times sine of 90 degrees. Okay. I remember for a turntable, you can treat that as a solid cylinder, like 1/2 mr squared. I'm going to throw that in right here. In place of the I, I'm going to call that 1/2 mr squared. Okay, and then alpha, solve for alpha. Okay, you got 0.7 meters times the force of 5 newtons is equal to 1/2 times 3 kilograms times 0.7 meters squared, all times alpha. Okay. Okay, then take this bit in parentheses, divide it down here, and I can solve for alpha. So it's that 0.7 times 5 divided by 1/2 by 3 by 0.7 squared. Okay. Cut through some algebra. I'm getting alpha is equal to 4.76. That'd be radians per second squared. Okay. Is that right? Then you could even have an extension question off that. You could say, well, suppose you're pulling for so many seconds. How fast is it rotating? And then that's where you go back to rotational kinematics. You say, well, I know alpha is this many radians per second squared. I'm pulling for so many seconds. Maybe it starts from rest. This might be 0. And then, hey, I can solve for that. How fast is it rotating? Radians per second. Okay, guys good? All right. You guys good with torque? Torque. Okay, equilibrium. I've got some good examples of this. These are good book problems. You guys can have some labs that involve torque. It's going to involve this equilibrium condition. Okay, so here's a big picture of equilibrium. Okay. Way back in the day, I told you guys this condition. I said, oh, if something's in equilibrium, the forces come to 0. And that's what we started with. Okay. Then we expanded on that and said, okay, well, suppose you have multiple dimensions, say like a 2D plane. Well, really, the forces have to sum to 0 in each direction. Okay. Do you guys remember like a donkey problem, like 2 people pulling a donkey? I think we used that setup to like solve that question. Okay. Okay. Now we're going to introduce this last condition. This is the other important condition. The turning moment, the torque also has to sum to 0, and the unit for torque is going to be Newton meter. Okay. Which, I meant to mention this too. You might want to call that joules because it looks like joules, but it's not joules. You always call it torque. The unit's going to be Newton meters. Okay. Okay, so it's just a thing. It's a totally different concept from energy. Okay, so Newton meters. Right, and now that could be for 2D equilibrium. If you ever go into 3 dimensions, like maybe you're an engineer one day designing some 3D structure and you want to put it in equilibrium, maybe it's like a 3D bridge, like a 3D truss, right? You have to have these 6 conditions, right? These 3 conditions plus these 3 conditions. So you have to have all 6 conditions going on to establish equilibrium. And you can solve for stuff like what is the compression in this part of the truss, something like that. Okay. Right. Guys, go back. All right. Next idea. Right hand rule. Okay, now I don't know how often we're gonna apply this actually in this class. I'm gonna stretch your guys' imagination a little bit here. Right. So, how about this? If you open a door, get a door going here. Okay, I got the hinges on this side. I got the handle right here. Okay. And I could like push or pull on this doorknob. So maybe I'm like pushing into right, that way, right? You get a door frame here. How about that? Like I'm trying to close this door. Okay. And I've got this radial size here. I'll call that R. Okay. And hey, let's say those are even perpendicular to each other. Okay. So R cross F, I could get like a turning moment, like a torque. Okay. You guys see that the axis of rotation would be where the hinges are. Okay. And there's be some turning moment here. Okay. You can think that like torque. Okay. Now, if you were bird's eye view from above, a bird looking from above, would this look like it was turning counterclockwise? Turning counterclockwise? You guys see counterclockwise, right? Okay. But what if you were down? You guys know we're on the 2nd floor. What if the floor was made out of glass and everyone down on the 1st floor was looking up? Would it look like the door was actually turning clockwise from their point of view? Okay, so is this door turning counterclockwise or clockwise? Well, it depends on what side you're on. If you're from above or you're from below, you've got different points of view. The birds say counterclockwise. Everyone down on the 1st floor says clockwise, right? Is that? So what's the direction of the torque? Well, there's a better, like mathematically, a better way to define torque, okay? Which is even though torque is sort of happening on this XY plane, to actually open up a Z axis and define it that way. And that's where this right-hand rule is going to come in. Okay? So right hand rule says if you put your fingers in the direction of the radial distance, and then curl your fingers in the direction of the force, or if you like, you can move your middle finger like this picture shows, then your thumb will naturally point to the direction of the torque along the z-axis, which is perpendicular to the xy plane. Okay. Now, what's that actually good for? Right? Well, one thing is that everybody's perspective stays the same. Okay? So whether you're birds up here or the people down below on the first floor, okay, everybody can agree on the direction of torque because I got R cross F, and see how my thumb would be pointing upwards. So you could define the torque for this picture as being like up instead of down, and everybody could agree on that. Okay, that's it. Another reason that this is good mathematically is because okay, let me show you guys some real fancy math, but this is gonna be good. Okay. Flip over screen 2 here. Which is a predecessor before I showed the real fancy one. We show you guys the animation of what I've been talking about. And so animation here. All right. So the red vector, these are all vectors, right? The red vector is some radial distance. The dark vector is like a force, and that light vector that's popping up and down on the z-axis could represent the torque. Right? Again, it's showing torque as like an arrow vector, although maybe more intuitively it could be like a counterclockwise or clockwise type motion, right? But it's the mathematical way to think of it. You guys see a right hand roll going on, right? You guys see a right hand roll? Okay. So sometimes your thumb is pointing up, right? That's right. Sometimes your thumb is pointing down, right? You guys see that? Right. So what's a really fancy math application of this? Suppose you have vectors in 3 dimensions. Now here I pulled up, I found this on YouTube. This is an example for cross products for it's some organic chemistry video. You guys ever learn matrices in a math class? Matrices, work matrix, maybe? Okay, well, if you ever come across this, I'm not going to fully delve into this, but I'll show you guys a little bit. Okay. At least enough for you to be okay, familiar with this kind of here. You guys see that vector A is defined as 5, -4, 3. Let me jot that down on this paper over here. It's showing. Hold on, make sure I'm sharing my screen here. Yeah, okay, we're good. All right, so copy down vector A is 5, -4, 3, and vector B is -7, 2, -8. About like that. Okay. Now I'm gonna flip my screen over, but flip back to let this finish off because I want to draw you guys the picture of what that represents. Okay. So I just copied this down. Oh, instead of A and B, I called it R and F because I'm going to cross those two. It's going to be R cross F. He's going to do A cross B on the video, but I'm going to do R cross F. That's the same idea. Okay. So I need some axes. We get an x-axis. Here's my, oh, here we go. A y-axis and a z-axis. Okay. So you guys see an xy plane right there, and then the z-axis, right? It's at three dimensions. Okay. So suppose I have a nut at the origin point. Right? It's like rusted over. We need to apply some torque to like break the rust. Right. So I got a radial distance 5, -4, 3. So here's 5 on the x-axis, 3, 4, 5, -4 on the y. So I got 5, -4, and then 3 on the z-axis. Okay, that's like kind of a sort of yours, right? Okay, so this could be like the end of the handle of this wrench. Right, in 3 dimensions, this wrench is like wrapping around and wants to do it. Okay, so we got this wrench set up, right? So this point right here could be like 5, -4, 3. About. Okay. So this is the end of the wrench. Right? And then we're applying a force also in 3-dimensional space. -7, 2, -8. So here's -7 about 2, -8. That's like way down here. Okay. So from the origin to this point is like the direction of the force. But I'm going to take that, apply it right here at this handle. So this force is in 3 dimensions, applying it kind of down here. So here's my R. Here's my F. Okay. Now this is a crazy 3-dimensional space example. Okay. But there's some torque that's being applied to that nut. Okay. And these vectors probably aren't even perpendicular to each other, but if they were, it would be maximizing the torque, right? But how much torque exactly are we getting? Okay. Well, you can get this with a cross product, and mathematically, you can find a cross product using matrix math, right? Which is what he's doing here. So this involves determinants, this sort of thing. We're not exactly going to do like this level of detail in this class, but again, just to see if this is here, okay, he's going to get some result. Ah, there you go. Right, so that I, J, and K are X, Y, and Z values of the torque, right? And then remember that torque is perpendicular to the plane that it's actually acting on, like clockwise or counterclockwise. You guys kind of get that? All right. Back over here. Okay. Okay. Now this is related to this idea of angular momentum. Right? I'll show you guys the connection here in a minute, but just for now, angular momentum. This is analogous to just regular momentum. You guys remember regular momentum was mass times velocity? Okay. Well, the rotational equivalent is rotational inertia times angular velocity. And this is a vector quantity, and it's also conserved, just like regular momentum was. Those are also true for regular momentum. Okay? So the classic question with this is the ice skater question. If I ever mentioned the ice skater problem, I do want to show you guys a quick Paul Hewitt here. Let's find Paul Hewitt.
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotation inertia or a little? How about when I pull them in? A little? So if I get here rotating like this and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Woo! Woo! Okay. You see such thing? All right. All right. You go to the you go to the ice follies, you see the skaters turning around like that, they're spinning, 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 spinning. And when they're spinning, they pull in like this, yeah? Go fast, 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 and then they come on. Da, 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 da. People think they're going like that for applause. You know what they're doing? They're trying to save them from breaking their necks. You increase your rotation. Isn't that neat?
Yeah, so what's conserved there is angular momentum, right? So the product of these two things. Right? So say like when this ice skater has her arms way out, her mass is distributed really far away. She has a huge rotational inertia, and she might be spinning, but just really slowly. She has a small angular velocity. But the product of those two is conserved. So when she pulls her arms in, now her mass distributed really close to her. It's a very small rotational inertia, which results in a large angular velocity. Right? Hey, do you think it would take some work to pull her arms in to go from the left picture to the right picture? Take some work. Do you think she's therefore putting some energy into that mechanical system? Right? Do you think she has more kinetic energy, 1/2 I omega squared on the right than on the left? I bet she does. I bet she has more rotational kinetic energy over here, which is like 1/2 I omega squared, analogous to 1/2 mv squared. Right? But yeah, this is conserved. We go. Okay. There is actually a angular momentum associated with a point mass. So suppose you have a point mass and it's headed towards like, we have like a swivel stick here. Do you guys see like a point up here, like X that's going to rotate about? Okay. And maybe you want to, there's some kind of collision going on. Maybe it's elastic, inelastic. Maybe you're told one or the other. Right? And find out, hey, how fast is this going to rotate after the collision? Okay? It has to do with what kind of collision it is. It has to do with these mass. It has to do with where this mass crashes with this swivel, right? So yeah, MVR could represent the rotational inertia of that system, right? And that would be one important step to go on and figure that out. Okay. Okay, so what's the connection between torque and angular momentum? Okay, so suppose you go back to that turntable, okay? And you have a string wound around, you're pulling with a constant force at this constant radial size, which is a constant torque, which means it's going to speed up spinning. Speed up spinning. Okay? So constant torque. Okay? If you apply that constant torque for a certain amount of time, then that turntable is building up more and more angular momentum, just like that ice skater. Okay? Well, the ice skater was conserved, and here it's not conserved. It's changing. Okay? You call this an angular impulse. Call it like that. Right? Okay? So yeah, so and if you find the area under this curve in terms of the units also match. Right? So both these graphs could be referring to the same story, just from different points of view. The graph on the right is how much angular momentum that turntable would have. Maybe it starts at rest, so it has nothing. Okay? It speeds up faster, faster, faster. In terms of the slope of this curve also represents the torque. You see how this constant slope and this constant torque, so that could be the same thing. So again, yeah, both these graphs could be referring to the same story, just from different points of view. Okay, guys with it? All right, just got a few slides left. Okay, let's look at the physics of a ball rolling down a hill. Now, we'll look at this from a few different points of view. I've got like the dynamics free body diagram point of view going on right here. And then the next slide, I've got an energy point of view. And it's different setups, but they lead to the exact same outcome. And the question could be, how fast is the basketball moving at the bottom of the incline? So suppose you point a radar gun at the basketball down here at the bottom. How fast is it moving? Okay. Well, how do you figure that out? And I've got two different methods that lead to the same outcome. So start with this this forces point of view. So this basketball has three forces on it. It's got its own weight. Right? It's got a normal force from the surface. And it's also got a friction force. See, if there was no friction force, it actually would not roll. It would just go down. It would look like a knuckleball, which would look really weird, right? But if anything's rolling down, that you need a friction force to induce that rolling. Okay. Also, notice how I haven't actually drawn the forces all at the center of mass. Right? I did for the weight, but not for these other guys. Right? Like the friction force, I actually drew it acting at the surface, right? And that's important for torque, for like a turning moment. Right. So what do we know here? You could figure out that the torque is equal to this expression. Now, sort of show you guys how. Right. So mg is the weight, that's like the force, okay? Acting at some radial along r. Now, if this were a perfect vertical wall, it would just be r. But I need times sine of theta, right? So this angle theta is equal to this little theta up here. It's the same angle, right? And then here's your lever arm. You can think of it like that. Right? You can see if I draw a really short horizontal line, that would be the lever arm, kind of like the width of the door, right? So there's your r cross f, right? Here's your r cross f. Right? And you guys know that torque is also equal to I times alpha. Now, I for a basketball, remember it was 2/3 mr squared rotating about the center, but this is not rotating about the center. It's rotating like on a surface like that, right? Okay. So I need to use the parallel axis theorem version of that, right? Anyway, you crunch the math and it ends up being this expression. Okay. Is that right? Now, if you look at this from a energy conservation point of view, this is the way I actually prefer to solve this because I think it's a lot more straightforward. Okay, so you can say at the top of the incline, it's all potential energy, mgh. If you like this h is equal to L times sine theta, that could be helpful. Okay? And at the bottom, it's kinetic energy, but it's actually two kinds of kinetic energy. Some of it is linear kinetic energy, right? What's the kinetic energy just moving in a straight line, right? But there's also some energy that goes into making it rotate. Now, this rotational kinetic energy, I'm going to treat as rotating about its own center of mass. So I'm going to use the regular 2/3 mr squared for rotational inertia. Right? You crunch the numbers there, you get the exact same speed of the basketball at the bottom of the incline. Okay. Right. Thanks for that. Right. Oh, and finally, last slide. What if we have a race between all these different objects? Okay. So I'll have one lane that actually is truly frictionless, and I'll put an air hockey puck on there. So we can compare everything to that. So this one goes from all potential energy to all linear kinetic energy. And I know what its speed is going to be at the bottom. Does anybody know its speed at the bottom in terms of its height? It's square root 2gh. You guys remember that? Okay. Now that's only true for the air hockey puck. Because all these other objects are on a surface that has some friction, some static friction, which means that they're going to roll. Okay? And so some of the energy goes into that rotation. But it's proportionally more for objects where the mass is distributed further out, but like here, so like the bowling ball could roll down really fast, but the ring is going to take a long time to roll down. Okay. Actually, if I had like a top type setup, so like a looks like that. Okay. Let's just compare the bowling ball to a basketball. How about that? Bowling ball to a basketball. Okay. Now the mass and radial size end up canceling out. If you want to just focus on the kinematic motion, right? But the distribution of mass ends up being important. So here's the bowling ball. Here's the basketball. If there's no frictional losses, they could do that for like 1,000 years, but the basketball would always have slower motion than the bowling ball. The bowling ball is kind of like if you take that meter sticks I've passed around that has the masses really close in, put those on a hula hoop. The basketball is closer to the situation of if you take the meter stick with the masses really far out. Right? You see it's the one with the small rotational inertia, really easy to get rolling. You want the large rotational inertia? Really hard to change this rotational state of motion, right? All right, so let's take us right to the bell. So that was a good pause point today. I'll get more fun stuff for you guys lined up this week.